Hello, everybody, and a warm welcome to this very special 5x15 event this evening. It's a delight for us to be hosting this special Stargazing Stories evening as we journey through the cosmos from our nearest neighbours to the furthest reaches of the universe. And today, of course, it's May the 4th, which is Star Wars Day, so it couldn't be more fitting for this gathering. Have you ever wondered what would happen if you fell into a black hole? How big is the universe? How did it begin? And indeed, how will it end? Well, these questions and many, many more are answered in the Illuminates series of accessible guides written by astronomers at the Royal Observatory Greenwich. And tonight we're really delighted to be collaborating with them and four of the authors who will be telling their extraordinary stories and telling us about their incredible work. The Royal Observatory Greenwich is the historic home of British astronomy, Greenwich Mean Time, and the prime meridian of the world. So it's a real honor to be working with their astronomers, and details for the books are in the chat. Tonight's going to be a 4x15, and a huge thanks to the team for making this possible, and to the hundreds of people that are logging in and watching along tonight. I know we're in for a treat. So first up, we have Dr. Emily Drabek-Maunder, author of Planets in the Illuminates series. She's an astronomer, an astrophysicist, and a science communicator, and she's currently the senior manager for public astronomy at the Royal Observatory Greenwich. And her talk this evening is about the incredible and inhospitable planet of Venus, named after a Roman goddess. But what is it about this planet that makes it so inhospitable to human life? And why is it an unlikely starting point for our search for alien life? So over to you, Emily. May the 4th be with you.
Thank you very much. And it's really lovely to be here this evening. So in this talk, I'm going to focus on one planet in particular, our closest planetary neighbor. That's also probably the most terrifying planet in our solar system, the planet Venus. So this planet has an incredibly misleading name. You would expect that a planet named after the Roman goddess of love, it should at least be hospitable to the human life. However, this planet is a prime example that love does indeed hurt. If humans ever do travel to Venus, the question to ask yourself isn't, will I die, but what's going to kill me first? So before I get into why this planet is so inhospitable to human life, I just want to mention that we didn't always know that Venus is such a hellish place. For many years, before astronomers ever sent spacecraft to study this planet up close, scientists imagined and even dreamed that the planet Venus was similar to the Earth. In the past, Venus has been called Earth's twin, and there is actually some truth to this. Venus is a rocky planet like the Earth, which means that it has a surface that we could technically stand on and explore. It's similar in size to the Earth. It's actually a little bit smaller than our own planet. And Venus is a similar distance to the Sun. It's just on the inner edge of what we call the habitable zone in our solar system. And the habitable zone is this region around our Sun. That means if a planet is in the habitable zone, it means the planet should be roughly at the right temperature for there to be liquid water on the planet. And so, of course, liquid water is one of the things that we need for life. Now, because of its similarities to our planet, Venus seems like this great prospect for having a similar climate to the Earth. All the way up until kind of the late 1950s and into the 1960s, astronomers dreamed of kind of peering below Venus's thick clouds and finding things like tropical jungles that could be teeming with life on the surface of the planet. It was with that belief that astronomers actually began sending spacecraft out into the solar system. So the hope was to find a planet in our solar system that was similar to the Earth. And actually the first interplanetary spacecraft ever sent out into space was to the planet Venus, and it was called Mariner 2. And Mariner 2 arrived at Venus on December 14th, 1962. Now, I want you to imagine the hope that the scientists must have felt when that spacecraft was arriving to Venus. And there must have been a great amount of anticipation as well. And yet, what the scientists found was a planet that was nothing like the Earth. And those thick clouds that I mentioned before that we can actually see from the Earth, so these thick clouds surrounding the planet Venus, they're actually trapping heat onto the surface, and that ends up creating surface temperatures on the planet Venus that are hotter than an oven. So our dreams of this Earth-like world were utterly shattered. But let me tell you what Venus is actually like. I'm going to do this by detailing a few different ways humans would not be able to survive if we did ever travel to the planet Venus. As an astronomer, I'm just going to say it right now, I'm afraid I cannot recommend this planet as a holiday destination, and I'll explain why. So as you travel in your spacecraft out to the planet Venus, the first thing you're going to notice are the beautiful clouds that surround the planet. Let me actually just bring up a picture of the planet. So you're going to notice these beautiful clouds that I mentioned, and this is what Venus looks like from Akatsuki, which is a spacecraft in orbit around the planet. The tranquility of Venus's appearance is really deceptive. These clouds, which you would need to pass through to reach Venus's surface, are actually made up of droplets of sulfuric acid. The clouds are actually acidic enough to be somewhere in between car battery acid and stomach acid, and they would easily be caustic enough to burn a hole through human skin. Now, the clouds aren't the only thing that you need to worry about if you're going to this planet. There's a host of other problems that we would run into. So of course, there's a lack of water on Venus, and that's something that certainly humans need in order to survive. But also Venus's atmosphere is mainly made up of carbon dioxide, and carbon dioxide is great for plants, but unfortunately to humans, it's poisonous to us. So we wouldn't be able to breathe the atmosphere on the planet. On top of these things, Venus is also incredibly hot. So I mentioned earlier that the planet is hotter than an oven. So the types of temperatures I'm talking about are upwards of 500 degrees Celsius, or around 900 degrees Fahrenheit. So to put that into perspective, if you were skydiving from a plane flying over the planet Venus, you would probably cook before ever reaching the ground. I know that's a terrifying thought. But even on top of all of these things, there are incredibly high pressures on Venus's surface. So the pressure experienced at the surface of Venus is 95 times higher than the pressure on Earth's surface. And so that's kind of like being about 1 kilometer or 3,000 feet below Earth's oceans. It's a similar sort of pressure. To put that into perspective, the deepest scuba dive on record by a human is only a third of that depth. And even at that depth, humans are at risk of their lungs collapsing from the pressure. So the pressures that you would experience on the surface of Venus would definitely be high enough to crush the human body. So if it isn't already obvious, humans have never been to the planet Venus, and I wouldn't recommend they ever go there for a holiday or otherwise. However, there are some robots that have been to the surface of Venus, and they've even survived long enough to send photos back to us. We actually do know what Venus's surface is like because we've seen it. And I'm going to show you actually a picture from the surface of the planet Venus. Now, the Veneer emissions from the former Soviet Union were a series of space probes sent to Venus from kind of the 1960s to the 1980s. The images may not be much to look at, but these are the only images we have taken of the planet directly from its surface. So what you're looking at is a desolate landscape that has been baked and hardened by the high temperatures and pressures on the planet. It shows that Venus is the harsh desert that we now know it to be. And also, just a fact for you, at most, the landers that were sent to Venus survived less than 2 hours on the surface due to the harsh conditions that they encountered. Okay, so I think we can all agree at this point, Venus is an awful planet. It's probably something out of our deepest nightmares as well. I could end my talk here on that very depressing note and leave you all with a terrible impression of this planet, but I want to end the talk on more of a high note for you. While Venus may be utterly hostile to us, to humans, this terrifying desert world may not actually be entirely hopeless in our search for life in the cosmos. Venus wasn't always the hellish world that we see today. For around 3 billion years, it's possible that this planet had temperatures more similar to the Earth, and it could have even had water at its surface, which of course, like I mentioned before, is a key ingredient for life, at least here on the Earth. This could have been enough time, so over that 3 billion year period, for some form of life to have developed on the planet Venus. So what exactly happened on the planet Venus to make its environment change so drastically is likely due to the greenhouse gas effect. So scientists think that it's possible that volcanic activity released lots of carbon dioxide into the atmosphere, and that carbon dioxide could have potentially trapped heat onto the surface of the planet that would have caused the water to evaporate and the temperatures to increase over time to what we see today. But if this is the case, if life did exist on Venus when it was more similar to the Earth, there is a possibility that life could have ended up evolving to somehow survive on the planet. Over time, it's possible that life may have migrated upwards into the clouds of Venus. So today, instead of life existing on the surface of Venus, some form of life could instead live in the clouds. And this isn't a new idea. Astronomers Carl Sagan and Harold Horowitz originally explored this idea in the 1960s when Mariner 2 was first sent to Venus. The upper clouds have temperatures and pressures that are more similar to the Earth, so they could be more habitable than the surface of the planet. Now, as strange and as far-fetched as this sounds, life existing in clouds is actually a thing here on the Earth. There's microbial life, or what we call microbes, on the Earth that actually live in Earth's clouds. And they mainly live in droplets, but there's also some free-floating microbes that exist in the atmosphere. These microbes can ride air currents and actually travel all around the globe here on the Earth. So this idea about the possibility for life existing in Venus's clouds has only picked up momentum with the discovery of a special kind of gas called phosphine that was found in the atmosphere of Venus, and that was announced in late 2020. So this is a really strange gas, this phosphine gas, and on the Earth, it's found to actually directly correspond to life, and in particularly weird and wonderful places on the Earth as well. So we find an excess amount of phosphine gas, we find it in stomachs of animals, but we also find it in relation to penguin poop, which is just kind of a weird fact about phosphine gas. But phosphine now has also been found in Venus's upper atmosphere, where the temperatures are cooler and the pressures are lower. So this has only renewed astronomers' interest in the planets and made them wonder what could potentially be producing this phosphine gas in Venus's atmosphere. Could it be chemistry in the clouds of the planet, or could it be something else? Could it be something like life in Venus's clouds? So we're living really in an incredibly exciting time in astronomy, one in which we're seeing more and more space telescopes and missions that are trying to understand our solar system and beyond. I think Venus is going to play an incredibly important part in the upcoming story about our solar system. It's our twin that verged down a different astronomical path that the Earth had. So in conclusion, I just want to say, yes, Venus is certainly the prime example that love hurts, but it may be our best chance for helping us understand if we're alone in the universe. Love may hurt sometimes, but it's worth it in the end. Thank you very much.
Emily, thank you so much. That was such a brilliant and engaging talk, and your book, Planet, is out now. So thank you very, very much for kicking us off. Next up, we have Dr. Ed Bloomer, who is the author of Black Holes in the Illuminates series. He completed his PhD at the Institute for Gravitational Research at the University of Glasgow, primarily trying to work out what happens when small black holes spiral into bigger ones. Since joining the Royal Observatory Greenwich, Ed has been involved in the full breadth of the organization's programming, but tonight he's going to be talking about what would happen if you fell into a black hole. What does that even mean? What is going to happen and what comes next? What even is a black hole anyway? Welcome, Ed. Thanks very much for being with us, and over to you.
Well, thank you very much for having me, and hello, everybody. It's lovely to speak to you today. So yeah, we're going to talk about black holes. They're a very weird thing. So I think to start off with, I'm going to jump straight in. I'm going to talk about what they are. One of the things I always try and get people to do is try and get rid of the idea that they may have in their head that a black hole is like, a black snooker ball, that it's this solid thing that just, it is black. Instead, what it is a region of the universe where the gravity is so strong that light can't escape it. That's what it is in simple terms. And we'll sort of talk a little bit more as we go through. Different people had different ideas about what we could eventually think of as a black hole. This goes back to 1784, when a minister, John Michell, proposed dark stars that were so dense that light couldn't even escape. They had a different understanding of light at the time, so maybe don't quite get the credit there, but really sort of Carl Schwarzschild in 1916 was the person that really put things on a very firm footing. And the maths is not particularly complicated in some sense, at least in the very simple cases, is that you can work out how much mass has to be in a small enough space, a small enough volume of space, such that light itself doesn't have the energy to get out of that gravitational well, and it gets pulled into the well, we call it a black hole. I mean, it's the thing that is the black hole. So the setup's fairly straightforward, but perhaps hole is a bad name for it. I mean, black is okay because light itself can't get out, but hole, they don't lead anywhere. And one of the things it's sort of a bugbear of mine that I try and correct whenever I can is, in the 50s, there was this idea of white holes. Okay, so you get black holes and this idea that gravity pulls things in. Well, wouldn't it be nice to have a balance? And we have a white hole and that's spewing out light into the universe. Well, I mean, within a few months, some of the targets that they thought might be white holes, and this idea raced around the world. Within a few months, actually, they got rid of that idea. But sort of 70 years later, we're still getting people talking about white holes. So that's a bugbear of mine, perhaps somewhat irrelevant, but maybe we'll tie it back in. The good news for if we decide to explore some black holes is they are, in theory, a really, really simple thing, a very, very simple thing for the universe to make. You need a bit of time and you need enough stuff squished into a small enough space, and gravity will do the job and collapse everything down into a black hole. The gravity is so strong that the atomic structure of material itself can't fight against gravity, and everything collapses into, in reality, a singularity, a sort of infinitely dense but infinitely small point in the center of the bigger region. So this is another thing. When we talk about black holes, a lot of the time people are talking about the region of influence, if you like. And then other people, if they're being pedantic, might be talking about the singularity, and they might talk about different things at different. So it's a bit of a strange one. It's one of those things you have to really nail what somebody's talking about at a particular moment in time. And this is important for us because what I intend to talk about is what happens, and spoiler alerts, it's all bad. What happens if we fall into a black hole that we're trying to explore? Just quickly, where do we find these things? Well, there's a couple of ways that the universe does actually make them. When supernovae go off, they throw off their outer layers while the inner layers collapse down, and that overcomes the atomic structure at that point. So supernovae are a good way of making black holes. And we have black holes in the center of galaxies. We've got one in the middle of our own galaxy. It's called Sagittarius A star. It has the same mass as about 4.1 million times that of the sun, or 4.1 million solar masses, as we call it. And we witness it indirectly. We see the orbits of stars pulled around the black hole because of its phenomenal gravity, but we don't see the actual black hole itself. Again, no light escaping. So what we technically might call the black hole is invisible to us. We might also see material falling in and creating an accretion disk, but we'll get to that. I just had a little animation from the European Space Agency, so I thought I would chuck that in here as well. So let's say, we'll come back to me. I'm going to watch you fall into a black hole. I don't want to be anywhere nearby, so I'm going to let bad things happen to you, I guess, which is not very noble of me, perhaps, but that's how we're going to do it. So as you fall into a black hole, actually what happens is there's other stuff falling in, and the immense gravity starts to accelerate you up to phenomenal speeds. You might reach speeds of, well, there have been observed in falling material at about 7,000 kilometers a second. So all this stuff rubs against each other, and the enormous friction generates huge amounts of radiation. So you're blasted by the radiation of stuff nearby. And that's one way to detect the black hole, not the hole itself, but the accretion disk that surrounds it. So you can sort of map out the surrounding regions, even if the black hole itself is not really visible to you. But we're going to imagine that your amazing spaceship can withstand that. You can decide whether or not you feel like you would want to go further, but you get to a point, you keep going down, and unfortunately, you can't maintain a stable orbit. In Newtonian mechanics, you can sort of maintain an orbit at whatever distance, but in reality, in fact, little instabilities mean that there is an innermost stable orbit for you. And if you cross beyond that, it's not to say you can't escape, but you can't set yourself up in a nice stable orbit and just keep yourself orbiting around and doing whatever observations you want. So there is a point at which things are going even worse for you, because you're inevitably falling further in. And then the black hole's gravity is so intense that space-time itself starts to get churned up like a whirlpool. Now, this is if the black hole is spinning. You know, maybe we're not going to examine a spinning black hole, but if it was, space-time itself churns around, and you need to try and fly in the opposite direction. The more mass, the bigger this effect, the closer in, the bigger this effect, and you get to the point where you would have to be going the opposite direction at more than the speed of light, even to stand still. So even without any of the other things going on in the black hole, that's not possible, and further you fall in. But let's say that, you know, there's no problem with that. We don't have to worry about what we call the ergosphere. And then you get to a point, well, we'll skip past all of the layers. There's a thing called the photon sphere, but sort of at its heart, really, we're worried most about the event horizon. And that is what David Finkelstein in 1958 described as a perfect unidirectional membrane. And that is the point at which, if you get closer to the center of the black hole, space-time is so curved that all directions lead into the black hole. Now, that's a wee bit tricky to think about, but what it means is that forwards is in, makes sense, but backwards is also in, and so is left and right and up and down. The curvature of space-time itself ends towards the black hole, so everything gets pulled in, and that's true even for light. So even if you could hover just inside the event horizon and you try to fire a laser light, you know, you got a laser torch or something like that, and you try and fire it directly outwards, that light itself will still curve around into the black hole, because there is no more direction. There's only one direction, and that is in towards the singularity. So I mean, you were gone or long before then. The tidal forces of the black hole, depending on the characteristics of a black hole, might have already stretched you out like a piece of spaghetti, pulled you apart. This process called spaghettification. So people always like to hear about that, or noodleization is the other way of thinking about it. But even if you could ignore that, there is the point of no return. The event horizon for anything, not even just your amazing spaceship that you're in, not even, maybe you were just flying in with a spacesuit, I don't know, but one way or the other, even if you were a particle of light itself, a photon of light cannot escape that region. So we don't get any information from that. That actually causes some problems, because the black hole itself is characterized only by its mass, which gives it a characteristic size. So for example, if you turned the sun into a black hole, you take all that mass, you turn it into a black hole, the radius, the Schwarzschild radius, after Carl Schwarzschild, 1916, that radius would only be about 3 kilometers. Okay, if you did it for the Earth, it would be just a little under a centimeter. Okay, so you turn the whole of the Earth into a black hole, it's a little under 2 centimeters across. I think that's 2 centimeters. For the moon, it's about the width of a human hair. So the size of it is determined by the mass. You can have a charge to it, and you can have a rotation to it. And the worrying thing for us at the moment is that causes some problems, because the information of things falling into it seems to be lost. But you might think, well, that's not that much of a problem really. But the problem for that is that quantum mechanical effects, Stephen Hawking believed that quantum mechanical effects, and he he worked this out mathematically, means that the black hole can evaporate over time, it can lose mass, and it can return information to the universe. So how does it store that information? That's unclear. And black holes can, anything can fall in. So if you've got two black holes and they merge, you basically end up with a slightly bigger black hole. But the question is, how do those singularities really merge right in the heart of it? So we're sort of inferring the existence of these things based on other stuff nearby. They fit very well mathematically with what we predict, but mathematically we haven't got a full description of absolutely everything. Now, I think my colleague Greg's going to be talking about eventual fates of things a little bit more. And I realize I've rushed through loads of different things. They're very weird things, I would say. But there's just one or two other little pictures I think is worth pointing out. There we go. There is the picture that we have of a black hole. There's another one which has some slight modifications, but this is the accretion disk around a black hole in a distant galaxy. It's about 53 million light years away. This is the synthesis of lots of different telescopes' data. It's not a photograph in a conventional sense. It's the Event Horizon Telescope Consortium, and this took years to produce. And again, there's actually lots that's really, really interesting and sort of amazing and groundbreaking about this picture. But for all intents and purposes, what we're seeing is the accretion disk surrounding, well, the invisibleness of the central black hole. Again, we can only map out the region nearby. We cannot, with any telescope, see the actual black hole itself. So this sort of cosmic donut shape looking thing is thus far as good as it gets. What I would like to, so it's all a bit bleak because basically I've just described it, ways we can fall in and no good, and then we don't get out and it's all terrible. So advice part one is certainly don't go anywhere near a black hole. Thankfully, there are no nearby black holes. In terms of the accretion disk, I just wanted to chuck in some extra big numbers because it's kind of cool to hear about this sort of thing. The most massive black hole that we have observed is called TON 618. It is about 18.2 billion light years away. But actually, the amount of stuff that's falling into it means that it's about 100 trillion times brighter than the sun. So even though it's an astonishing distance, it's actually, at least the accretion disk nearby, is bright enough to pick up. And this is actually one of the things that when people were thinking about white holes and possible candidates for that, I sort of dismissed it right at the start. But in fact, early white hole candidates were in fact very early active galaxies with a black hole in the center of it, with loads of material falling in, and it became very, very bright. So in fact, the white holes were, by sort of circulation there, were black holes. It's all black holes. And as I say, I think Greg is going to talk a little bit more about eventual fates, but the rate at which massive black holes evaporate, and this TON 618 is so large that the characteristic size of that event horizon is about 400 billion kilometers across. It is vastly more distant than the distance between us and, well, whatever planet you think of in the. I think it's about that equates to about 40 times the distance between us and Neptune, I believe. That's for the radius, so double that again for the diameter. It's big. It's big. You plonk that in the middle of the solar system, and you know everything's gone that we really care about. So that's all pretty depressing. But even worse than that is the rate of evaporation is so slow that it will outlast the generations of stars that are born and die. And the expansion of the universe means that the very end, interesting stuff in the universe may be just this graveyard of slowly evaporating black holes that dissipate into fundamental particles that are too cold and too separate to do anything. And then, well, that's the end of it. And I think on that note, I'll probably stop there and hope that someone else has something more, a little bit more lighthearted.
Ed, thank you so much. That was an incredible challenge for a 15-minute talk, and you pulled it off. That was brilliant. Thank you so, so much. So Ed's book, Black Holes, is out now, and the details are in the chat. And next up, we have Dara Patel, who's going to be talking about her book, Space Exploration. She's a space expert at the National Space Centre in Leicester. Prior to that, she worked as an astronomer and science communicator at the Royal Observatory, though she began her career as a secondary school teacher. Tonight, she's going to tell the story of the often overlooked Apollo 8 mission, which was the first time that humans left the vicinity of Earth over 50 years ago. The story is full of risks and camaraderie, breaking records, and it's also the story of a mission that eventually made it possible for humans to land on our lunar neighbor. So welcome, Dara. Thanks very much for being with us, and I will hand over to you.
Thanks very much, Daisy. So to begin with, I guess, for me, robotic exploration really has revolutionized our understanding of the solar system and beyond. But it's crude exploration that really excites me. And I think it's what draws many people to actually having a real interest in space. Now, not long ago, we celebrated the 50th anniversary of Apollo 11, the first time that people actually landed on the moon. And this December will be marking the 50th anniversary of Apollo 17, the last time that humans stepped foot on our lunar neighbor. And although most of us might recall the lunar landing mission, so Apollo 11 through to Apollo 17, one of the most overlooked missions has got to be Apollo 8. It conducted so many firsts, and it kick-started crude exploration in space beyond our planet. So what I'd like to do in the next few minutes is to share some of the stories and accounts of this mission and leave you with a sense of reverence for the spirit and achievements of this mission. So Apollo 7 launched in October 1968, and that was a crude test of the command and service module of the Apollo spacecraft in Earth orbit. So the Apollo spacecraft was made up of essentially 3 modules. The command and service module were 2 of those 3 parts. In follow-up to Apollo 7, Apollo 8 was planned for early 1969, and it would test all 3 parts of the Apollo spacecraft in low Earth orbit. So the command and service module, but also the lunar module. To put it into a bit of context, the command and service module is where the crew would be housed, and it would serve the sort of propulsion, the life support, and the electric systems. And then the lunar module is the part that would land on the moon. Now, following Apollo 8, there would be Apollo 9, and it would conduct the same thing, the test of the entire Apollo spacecraft, but in medium Earth orbit. So it'd be testing this at a more distant kind of reach from the Earth, somewhere a bit further out in space. Unfortunately, there were delays on the lunar module's production, and rumours were sparking that the Soviet Union were going to be ready to launch a crewed lunar orbital mission. And so this spurred NASA in August 1968 to actually conduct a test of just the command and service module without the lunar module, but not around the Earth. Instead, it would be a lunar orbital mission, the first time that a spacecraft would be taken away from the Earth. And this they proposed to do by the end of that year, by December 1968. Now, the original crew of Apollo 8 was James McDivitt, David Scott, and Rusty Schweickart. They preferred not to change their task. They had been training really intensively on the lunar module, and now that it wasn't ready to be used, they opted to fly on a later mission where they could actually put their training into better practice. When the same question was proposed to the then crew of Apollo 9, Frank Borman, James or Jim Lovell, and William Anders, they were quite happy to switch. And so the crews of Apollo 8 and 9 were actually changed over. And that meant that Borman and his crew had 2 to 3 months of less training than originally they might have planned for. Can we bring up image 1, please? So Frank Borman, he was the commander for Apollo 8, and he was a test pilot like many astronauts of the time. He'd flown in NASA's previous crewed program, the Gemini program, and he served as commander of Gemini 7. This was a long duration spaceflight. He'd spent 14 days in orbit around the Earth. And at the time, this was double the length that anyone had spent in space before. And it stood as the longest spaceflight duration record for about 5 years. Now, Jim Lovell, he also flew with Borman on Gemini 7, and now they would be reunited on Apollo 8. Lovell actually went on to become the commander of Apollo 13, the only lunar landing mission that didn't make its target. In fact, it turned into a very ill-fated rescue mission when an oxygen tank explosion in the command and service module of that spacecraft actually caused the astronauts to use the only other available part of their spacecraft, the lunar module, as a lifeboat to return back to the Earth. And although he served as backup crew for other missions, William Anders only had one spaceflight, and that was with Apollo 8. Can we bring up image 2, please? So the crew of Apollo 8, they launched on the monstrous Saturn V rocket. Now you can see that the rocket is mostly filled with fuel, and the top part is the only bit that really houses the spacecraft, and it's composed of the command and service module and the lunar module as well. Though remember, for Apollo 8, it was only the command and service module that was launched because the lunar module wasn't ready. And with no lunar module, had Apollo 8 encountered the same fate as Apollo 13, i.e. irreparable damage to the command and service module, they would have been literally at risk. There would have been no potential lifeboat in the lunar module. They would have ended up essentially dying in space. Now, to date, the Saturn V remains the most powerful rocket to have ever operated. It's a 3-stage rocket standing at 111 meters tall. That makes it taller than the Statue of Liberty or the Big Ben clock tower. Now, this rocket could launch the weight of 4 American school buses to the moon, and the crew of Apollo 8 were the first to experience a ride on such a powerful rocket, a rocket that was required to leave the gravity of the Earth and reach the moon. Now, Borman shared his recollections of launch in the Saturn V rocket. He mentioned that it got really hard to breathe, and it was almost impossible to move as he was pushed back into his seat. He felt his eyes flattening out, giving him tunnel vision, and described it as a really unusual feeling. Anders also described the incredible thrust that was felt at launch, and he shared the following anecdote. So as the first stage of the rocket was burning its fuel, the acceleration pushed the crew back into their seats with a force of 6G. In comparison, take a Bugatti Veyron sports car, you'd experience a G-force of just 1.3 if you were braking from 100 down to 0 kilometers an hour in less than 2.5 seconds. So the astronauts were actually experiencing 4 times higher G-forces, and not just for seconds, but for minutes. He continues his story, Anders, and he says that when the first stage of the fuel was spent, the engine cut off and waited for the first stage to essentially be ejected. And at that moment, the G-forces suddenly dropped, and he felt fluid sloshing in his ears, and that gave him a sense of literally being catapulted across the spacecraft. Instinctively, he threw up his hands in front of his face, something he calls a third-level reaction, and at that very moment, the second stage of the rocket ignited. The G-forces snapped back in, and it forced his gloves right into his helmet visor, causing a gash across the faceplate. He was incredibly embarrassed. He feared that he'd be ridiculed as a rookie. But once the crew were in orbit and they'd taken off their suits, he noticed that his crewmates, Lovell and Borman, also had gashes across their helmets too. He definitely wasn't the only rookie on this new ride into space. We have image 3, please. So what you'll see here is Borman inside their Apollo 8 spacecraft, and it was captured by an onboard camera. Halfway to the moon, the crew actually conducted the first of several TV broadcasts from inside their spacecraft. And this would have been the first TV broadcast from beyond the vicinity of Earth. They also conducted another telecast on Christmas Eve whilst in orbit around the moon. And it was anticipated that it would be the most watched TV broadcast at the time. As many as 1 billion people would tune in, about 1/4 of the world's population at the time. So NASA told the crew to come up with something appropriate. And after much contemplation, the crew decided to read from the book of Genesis. Borman actually recounts that the crew were really convinced that it was the most appropriate thing to do, because there's this great sense of awe that the universe is just much bigger than us all. It's too orderly and it's too enormous not to have some sort of divine creation. And in fact, it's something that I've come to contemplate the more my understanding of science improves. Image 4, please. So I mentioned earlier that one of the risks was that Apollo 8 didn't have a lunar module, something that could potentially be used as a lifeboat in case something went wrong. But actually, some of the biggest risks were the maneuvers that this crew had to perform on their way to the moon and on their way back. Now, the Translunar Injection is a maneuver that they needed to perform to be captured into lunar orbit. So they'd burn their thrusters whilst on the far side of the moon with no contact with anyone on the Earth, and it would help to slow the craft down to ensure that it was captured into lunar orbit. Now, if they slowed down too much, they would end up crashing into the surface of the moon. And if they didn't slow down enough, they'd continue out into the solar system forever. And the same goes for the return to the Earth after orbiting the moon. The thrusters would need to burn to get them out of lunar orbit to escape the moon's gravity and direct them back towards the Earth. And again, this maneuver would have to be conducted whilst they were on the far side of the moon, with no contact with anyone on the Earth. For people on the ground, it definitely would have been much of a nerve-wracking wait. Now, you may have seen just there, each of the missions also had their own patch, and the Apollo 8 astronauts had their names and mission number 8 very artistically incorporated to show their flight path to the moon and back. Now, the crew spent 10 orbits around the moon before they performed that trans-Earth injection to bring themselves back to the Earth, and that maneuver was actually conducted on Christmas Day in 1968. So as they came back round from the far side of the moon, waiting to regain contact with the ground, eventually Lovell finally exclaimed across mission control, with much relief, I can imagine, "Please be informed there is a Santa Claus." Now, the crew even had their present from mission control, which was a turkey dinner with gravy in space. And Deke Slayton, the crew's boss, had also smuggled 3 shots of brandy on board for the crew. But they didn't drink that. They didn't want to be blamed for anything going wrong on their mission back, so they actually brought it home. Now, the crew of Apollo 8 were the first ever to see the far side of the moon with their own eyes, and they described the surface as being very distressed, marked with holes and craters and volcanic residue. So it was a very interesting first view of a different world. And when asked, what's the most beautiful sight you saw in space? One of the astronauts answered, a urine dump at sunset. You see, as their liquid waste would be discarded from the spacecraft and sucked into the vacuum of space, those droplets would freeze instantly into iridescent drops of ice, a little bit like glitter in space. It highlights the serene yet dangerous environment of space and the sanctuary that their spacecraft provided them. Image 5, please. But perhaps the most unique sight was when the crew were coming back around in orbit from the far side of the moon, and Anders spotted the blue marble of the Earth rising above the lunar horizon. He scrambled around the spacecraft to find a camera color film to capture the moment. He took multiple shots, and one of them has now been popularized as a photo called Earthrise. This has become one of the most influential images of the 20th century, and it's often credited for propelling the environmental movement that led to the first Earth Day being celebrated in 1970. And the greatest impact, according to Anders, is that we came all the way to explore the moon, and the most important thing is that we discovered the Earth. Apollo 8 was never intended to be so ambitious. It was originally planned as the first test of the Apollo lander in low Earth orbit. But actually, Apollo 8 allowed the whole program to be speed-tracked and the remaining tests to be conducted much quicker. So by early 1969, Apollo 9 was able to test the Command and Service module and the then ready lunar module in Earth orbit. And because they'd already been to the moon with Apollo 8, there was much more confidence in sending Apollo 10 as a dress rehearsal. Essentially, the whole Apollo spacecraft was sent all the way to the moon, orbited around, and short of landing, it came back. In fact, NASA purposely underfueled the lunar module on Apollo 10 to ensure the astronauts didn't get any cheeky ideas of attempting a landing and being the first to land on the moon. But just 7 months after Apollo 8, it was possible for Apollo 11 to land the first humans on the moon. And whilst the bravery of the 3 astronauts of Apollo 8 is not to be belittled, sometimes we do forget the hundreds and thousands of people that have worked in the background to make it all possible. Space exploration is truly a very collaborative endeavour, and it should unite humankind. We now have the Artemis Program, so led by NASA. This is a crewed lunar program, working with lots of space organisations and countries around the world in the hope that we'll return people back to the moon and this time establish long-term presence on it. It feels as though despite our technological advances, exploring space and the moon remains a risky test of human ingenuity and also astronaut bravery even today. But will 21st century exploration of the moon teach us something unforeseen about humanity and life? Or perhaps will it make us look back at the Earth like Apollo 8 did, in a very different, unexpected and revolutionary light, a light that somehow we've not seen it in before.
Dara, thank you so much. It's such an extraordinary story, and we absolutely loved hearing all about Apollo 8 and the amazing team behind it. So thank you very, very much for being with us. And finally, this evening, we have Dr. Greg Brown. He's the author of Stars and the Universe in the Illuminates series. He obtained his PhD at the University of Warwick, studying the untimely death of stars. And after finishing his doctorate, he began working in outreach, coordinating, and then building on his passion for science communication before joining the Royal Observatory Greenwich in 2017. So the stars in our sky may seem eternal to us short-lived humans, but nothing could be further from the truth. One day, the hydrogen fuel that powers stars will be used up and the universe itself will grow dark. So this evening, Dr. Greg Brown takes us on a tour of the distant future as we discover the eventual fate of our cosmos. Thank you very much, Greg, and over to you.
Good evening, class. Welcome to your first lecture in a course on advanced nihilism. Don't bother taking any notes, there isn't any point. Okay, to begin. One day, the universe will end. That's the end of your course on advanced nihilism. Thank you very much, and have a good evening. Okay. I can do better than that. One of the most impressive discoveries of the last 100 years occurred in the early 1920s. Edwin Hubble and Georges Lemaitre realized that almost every galaxy in the universe is moving away from us. And it's not that the galaxies themselves are moving. They are, but not in so coordinated a fashion. No, it's that the universe itself is expanding. Space is getting bigger. And the implications of that are quite wide-ranging and a little bit complicated, but there's one I'd like to focus on. What would happen if you pressed rewind on the video of the universe? Well, with the universe currently expanding, what would then happen is the universe would be contracting. Everything would be getting closer and closer together. The universe would be getting smaller and smaller, and eventually, taken to its extreme, everything would pretty much be bang on top of one another. The universe would be very small, very dense, and very, very hot. Now, for some reason, at some point, this changed. Something caused the universe to expand massively and extremely quickly. We don't know what caused it, and we may never know, but we've given it a name. It's called the Big Bang. You may have heard it being referred to as the beginning of the universe, but it'd be more accurate to say it's the beginning of the universe as we know it. If there ever was anything before the Big Bang, we don't know, and we may never know. But the really important thing is, everyone knows that anything that has a beginning also has an end. And the universe appears to be no exception. Now, I'm not suggesting that the universe is going to end tomorrow or next week or next year or even next millennium. We've got an extremely long time to go. Take stars, for example. Our sun will last somewhere between 10 and 12 billion years. It's about 4.5 billion years through, so about halfway. There are other stars out there like Proxima Centauri, the closest star to our own sun, which is a tiny red dwarf star. Stars like this can last for 10 trillion years, no problem. And that's 1,000 times longer than our universe has actually been around. No red dwarf stars have had the chance to die by natural causes yet. The universe is just too young. And what's more, even when those stars do eventually die off, they can be recycled. The material that makes them up can be turned into vast nebulae that are then crushed back down to create new generations of stars. Our own sun is a third generation star. We know that because the stuff that makes up you, me, and almost everything around us, carbon, nitrogen, oxygen, iron, gold, they are all have to be created in the cores of stars. But here's the thing. All of those stars need fuel. Hydrogen, to be exact. That hydrogen is converted through a process known as nuclear fusion into something called helium. And energy comes out. But when those stars are recycled, all of the hydrogen that's been used up has been lost. All of the energy they created is now out in the rest of the universe, never to return. Which means that the stars are slowly working their way through the fuel of the universe. And one day, it's going to run out. When? Well, sooner than you might think, actually. Cosmic dawn was the time when the first stars appeared in the universe. It happened about 100 million years or so after the Big Bang. Cosmic noon, then, would be the peak of star formation, when the most new stars are being created in the universe, the peak activity of our universe. And that is going to occur 10 billion years ago. It's already happened. 5 billion years before our sun was even born, the star formation rate of the universe was already starting to decline. Every generation of stars that comes from this point forwards is going to be smaller than the generation that came before it, until eventually there's going to be a trickle of star formation left. Now, this is going to take a long time, hundreds, thousands of trillions of years, and the stars that they make will last for tens, hundreds of trillions of years after that. But eventually, the stars are going to run out, and the universe is going to go dark. But here's the thing. That's not actually the end of the universe, is it? It's just the end of the luminous globes that are lighting everything up at the moment. What about the universe itself? Well, based on our understanding of physics, there is no version of the laws of physics that allow the universe to exist forever. Just can't happen, not as far as we know. And the eventual fate of the universe is going to come down to just two forces. Well, forces, because neither of them are actually forces, but that's a bit complicated, so we won't get into it today. The first you're very familiar with. It's the force that's constantly trying to turn your life into a slapstick comedy as you drop, trip, and stumble your way through your existence. It's called gravity. And it's constantly trying to crush everything in the universe down, make everything get closer and closer together until everything is confined into a small, dense, extremely hot space. Sound familiar? Yeah. It's trying to return things back to what the universe looked like at the time of the Big Bang. But it's being fought against by something called dark energy. We don't know what it is. We don't know how it works. We're not even certain it actually exists, but it certainly seems to. And what it's trying to do is it's trying to make the universe expand, accelerating the expansion of the universe, making it bigger and bigger, faster and faster. And the eventual fate of the universe is going to come down to which of these two forces win and by how much. If dark energy wins and wins by a lot, then the universe is going to end in a very, very abrupt way. We can't see the entire way through the universe. We can only see a certain distance through it. And that's because light takes time to travel. The universe has only been around for 14 billion years, so we can only see as far away in the universe as light has had 14 billion years to travel to get to us. Anything further away than that, we're going to have to wait for the light to finally reach us. Unless dark energy has its way. Because if dark energy has its way, then not only will the things that aren't currently visible to us will never become visible, but things which are currently visible to us will actually be pushed out of our view, beyond our horizon. That's because the light coming from them would eventually be in a race that's constantly getting longer because of the expansion of the universe, faster than light can make up the difference. It's in a race where the finishing line is constantly moving away from it faster than the speed of light, which means it never gets there. And the really scary thing about that is there's nothing to stop that. It will start with just the most distant galaxies in the universe, the bits that are so incredibly far away that might as well not matter, but eventually it will be only the local universe that we can see, then the galaxy, then our solar system, then our planet, and at that point you are mere moments away from the universe being smaller, the observable universe being smaller than the size of an atom. When that happens, the electrons that orbit around the nuclei of those atoms will no longer be able to feel the pull of the forces holding them together. Every atom in the universe will simultaneously self-destruct, mere moments before the universe tears itself to shreds in something called the Big Rip. The good news is that we don't think that's going to happen. The laws of physics of our universe don't quite match up with the laws of physics required for a universe that does that. The bad news is the alternatives aren't any better. If gravity wins, then it's going to eventually slow the expansion of the universe, reverse it, and create what looks like the very beginning of our universe again, as everything gets crushed down to an incredibly small point. Now, it's been suggested that that might, in fact, start a new universe, something called the Big Bounce. And it's even been suggested that our universe might just be one in a whole line of universes going back into the past and on into the future, each one being born from the ashes of the universe that came before it, but with absolutely no knowledge of any of the other universes in that long chain. Not really certain how much more comforting that idea is, to be honest. And then we get the possibility that either dark energy and gravity are perfectly aligned with one another, perfectly in sync, or that dark energy wins, but not by a lot. Well, in both of those situations, the universe will just sort of keep getting bigger until it becomes dark, cold, and empty. Everything that we know, all of the elements in the entirety of the universe, will slowly convert themselves into iron, the most stable element in the universe. Those spheres of iron that used to be all of the planets, stars, and other objects in the universe will eventually collapse in upon themselves to create black holes. And as Ed was saying earlier, eventually those black holes will slowly, incredibly, arduously evaporate over ridiculously long timescales until eventually the universe is empty and the heat death of the universe will be complete. So, how long do we have before this terrible fate befalls us? 10 to the 10 to the 120 years. It's quite difficult for me to explain in words quite how big a number that actually is. We are all astronomers, the people that you've listened to today. We're used to big numbers, happens all the time, but this is by far the largest number that I have seen in astronomy. To put things in perspective, 1,000 years, a millennium, is 10 to the 3. The universe has been around for about 10 to the 10 years. If you were to take every single atom in the universe and make it count 100 billion times per second from the very beginning of the universe right up until now, we would very recently have crossed 10 to the 10 to the 2. And this is 10 to the 10 to the 120. So what am I saying? Well, we've got some time. Thanks for listening.
Greg, thank you so much. That was so thrilling and mind-boggling and incredibly surprising and sort of brilliant. So we just loved listening to you, and I'm still trying to get my head around that number and just the scale of it. Thank you very, very much for finishing off the evening on such a fantastic note. So that brings us to the end of this evening's programme. We have had such a fantastic time working with the Royal Museums Greenwich and with these incredible astronomers. So a huge thank you to Greg, Dara, Ed and Emily for their brilliant talks. They're all incredible science communicators and scientists, and their books are out now. So do pick up a copy and find out more about their work. Thanks to Kathleen Bloomfield and thanks to Zara Capello at 5x15. We will see you all again very, very soon. But for this evening, it's good night from all of us and a huge thank you. Good night.